Hello, AP Calculus AB students. Mr. Record here, taking a look at example 9 from our topic 6.3. We're going to take a look one last time at finding the area under a curve using the limit process. And I know that you're probably pretty happy that this is going to be our last approach with this because it's been pretty tedious. I think we're just about on the brink of perhaps finding a shortcut. Now, before we introduce this example 9, I want to mention to you that it's no accident that our wonderful Greek symbol sigma eventually evolved into this sort of S-shaped symbol that we will from this point on refer to as our integration symbol. After all, they're both very similar to the Roman alphabet letter S, which means, or which the word sum starts with, of course. So therefore, calculus has a kind of a new way of asking a familiar question. So finding the area underneath the positive curve y equal f of x and above the x-axis between a and b can be written now using that new integration symbol. And you just simply have to decipher from that particular expression that f of x is the equation of that curve, and a is the lower left boundary, and b is the upper right-hand boundary. And so if we take a look at our example 9, it says evaluate the following definite integral using the limit definition. So we have this integral symbol with a lower boundary -2 and upper boundary of 1 of 2x. Basically, the key players in the game are there in this problem. In other words, the function f of x is going to be x squared. We're knowing that a is -1, a would be -2, sorry about that, and b is +1. So we basically have the same information that we had in a couple of our previous problems. Now all that we need to do is start the process. So if you remember, the first thing that we find is the width, and we have a formula for that. It always goes b minus a, all divided by an unknown number of subintervals n. And as you can see, this will reduce to 3 over n. And then if you recall, we had a formula for height as well. Now with the height, you have a couple of things that you have to do. First of all, f of, and now in this particular problem, you notice that your a is -2, so you must start at -2 and add your width 3 over n, and at this point you have a choice. You can either use the right endpoint approach or the left endpoint approach. We've shown that you're going to get the same answer, so then you basically say, do I want I or do I want I minus 1? Last problem, do you want to try for the left endpoint and put an I minus 1? Of course you don't. You never want to do that. So we're just going to go with I every single time. And so at this point, we would go ahead and figure out what the height is by taking 2 times this value of x. So 2 times the quantity -2 plus 3i over n, of course, would produce a -4 plus 6i over n. But I think at this stage, we could just leave it written like that. So what we're going to do is then say our area is equivalent to the limit as n approaches infinity of the summation as I goes from 1 to n. And then we're going to take our width and height and multiply them. So I'm going to start off with the height here and multiply that by our width, which is 3 over n. All right. Now, what I would suggest at this stage is we clean this limit expression up a little bit. I'm always a big advocate for getting our common denominator. And so we do that first, and we would find that this -2 would need to multiply itself by n over n. And so we'd have -2n plus 3i all over n. And then, of course, our width 3 over n is in the back there. Now, what that allows us to do is start factoring out some things in front. We see that the 2 times 3 is a 6. That can come out to the front of the summation. Down in the bottom, n times n and n squared can come out in front of the summation. So we're basically looking at a 6 over n squared that we're bringing to the forefront, and the summation now is only going to act upon negative 2n plus 3i, which is fine because we certainly have formulas for that. All right, hopefully this is making sense. I'm going to go ahead and put a little line here, and I'm going to continue the work here in a right column. So what do we have? Well, our limit still is hanging around, and our 6 over n squared is hanging around, but now we can start to employ our summation properties and formulas. The summation of negative 2n. Well, remember, negative 2n basically acts as a constant. You'd multiply that by an n, which essentially creates an n squared there. Next, we have plus 3. The summation of I is going to be the formula n times n plus 1, all divided by 2. As soon as you're comfortable to find the limit expression answer, you can write your final response. So we tend to do a little bit better job in finding the answer to the limit once we have a common denominator. So I would suggest that we obtain that common denominator of 2 here. And that will be obtained when we multiply this negative 2n squared by 2 over 2, which produces the fraction. And then I'm going to go ahead and start the process of multiplying through by this 3n. See, this one's actually a pretty easy one to not only find the limit's answer, but to really express the entire value here on the right side of the limit statement without having to use that gray little squiggly mark that indicates all of the terms that don't really matter. So we're going to go ahead and write our final expression, and that would give us negative 1n squared plus 3n. But if we distribute the 6, we're going to get negative 6n squared plus 18n, and then a denominator is 2n squared. And then finally, we agree that the degree on top and the degree on bottom are the same. So we divide the coefficients in front of those terms. Negative 6 divided by 2 is indeed negative 3. And that will serve as the answer to this particular problem. Now I want to discuss something before we close out. Notice that our answer is negative 3, which you might think is a little bit unusual. Can you have an area that's negative? Well, if you'll allow me just a moment here to sketch this graph, and I don't think that this is a very difficult one to sketch. I think we can see that if we graph the function y equal 2x, we know that that is going to be a line. And that line is going to have a y-intercept of 0 and a slope of positive 2. So in other words, that line is going to look a little something like this along this interval, negative 2 to positive 1. So when we find the area between this curve, and I know I'm using the term curve very loosely, I have some space that's below the x-axis, I have some space that's above the x-axis. If we find the area of the space right here, a triangle that's 1 by 2, we see we can use the formula for the area of a triangle, 1/2 of the base times the height, and we get 1. And that's how much space there is inside of that particular triangle. Now, when we do the same thing to this triangle, things are a bit different because we have a base of 2 and a height of what would be 4, which in turn gives us 1/2 times 4 times 2, which is 1/2 of 8, which is 4. But because this space is underneath the x-axis, we treat it as a negative, and that's going to be a new idea that we're going to have to slowly, gradually get used to. And when you take the sum of those two, you certainly will get this answer of negative 3. What's nice is that this whole process is going to know that part of this area was negative, and it will account for that accordingly. Now, I'm going to tell you together, this is the last time that we're going to use this longer method, because there is a shortcut coming along the horizon that we're going to discuss, but what we'll need to do is understand how to operate on that particular integral expression first. A lot of really fun times coming ahead. Make sure you join us for some of our future videos. Thanks for joining, and we'll see you next time.